Here. All right. Good morning. Happy Tuesday, I guess it is. Let's see here. Okay, so we talked about, do you want to have a test or 3 tests or 2 tests? We're going to stick with 3 tests. One's going to be like a mini test at the end of the term. So I do want to have a test. I'm going to put it off until we've covered exponents and logs. And so test number 2 on November, I'll say, got my calendar over here, Tuesday, so it's going to be on a Tuesday, November 17th. Okay. Same format as before, so I'll post the PDF. You work through it, you upload your work to Gradescope, and that's it. So I'll give you guys a practice test, but it is going to include another section or another chapter. So we're not quite ready for it yet. It might be a little overwhelming, but I'll start working on that and then put that out to you guys. So just a heads up, we're not going to have a review day for this test. So there will not be a review day for this test. Okay. But a practice test will be made available. But a practice test will be made available. Oops. Okay, so just a heads up that we're not going to have time to do a review day. Usually that's what I like to do. But time. All right. So, and then what we'll do is hopefully we'll do like a mini test, so quiz, I guess, right at the end of the term. So it's not going to be worth very much, but I just want you to have a chance to have seen the newest stuff on a test before we head into the final exam. So we will do a mini test number 3 at the very end of the term. So that we've seen all the material before the final exam. Or so that you have a chance to see all the material on a test before the final exam. Okay, so I'll call it a mini test. It'll be worth a little bit less because it's going to be on trig, so we don't cover a lot of material in trig, but it's going to be quite different. So I want you to have a chance to see it on a test. Okay. So for review, just kind of briefly, we finished inverses last day, so that took up a fair chunk of time. And then we moved on to quadratic functions. Quadratic functions look like f of x is ax squared plus bx plus c. This is called the general form. Okay. The standard form is f of x equals a times x minus h squared plus k. So this is the standard form. To get from the general form to the standard form, there's some benefits, or there are a lot of benefits actually, to working in standard form. But to get from the general form to the standard form, we have to complete the square, which is a little bit tricky when we're first getting started. And we actually had to pull that from 1.5. So, so check your notes from last day. Make sure that that kind of makes sense going from general form to standard form. Because once we have it in standard form, then it's easy to find the vertex, right? And it's easier to kind of see the shape of this thing. So the vertex is at hk. Notice that this is x minus h, right? So if you have x plus 3, for example, your h would be -3. So just a heads up, right? So your vertex here is at hk, so that is really nice to know. The vertex is at the point h, oh, clean up my hk, right? And so that's really useful. We also know some things about, this is the same a, right? So if a is positive, then it's pointing up. If a is negative, we've got a parabola pointing down. So if a is greater than 0, then the parabola is pointing up like this. Whee! And if a is less than 0, then you've got a parabola pointing down like this, right? So the vertex, remember, is the kind of the peak or the valley, depending on if a is positive or negative. And then, so if a is positive, then the vertex is going to be the minimum, right? Whereas if a is negative, then it's pointing down, then the vertex would be the maximum, right? And so we can use all that information to learn a lot about this function. Okay, I want to make sure that I show you on Moodle. Okay, so I posted, I split up the notes from last day, polynomial functions, into part 1 and part 2. So we're just wrapping up part 1 today, and then we're going to head into part 2 for this week. I also posted little assignments for 2.7, 2.8, and 3.1. Okay, so make sure you work on those. Those are due on November 10th, so next Tuesday at midnight. Let's see here. Assignments for 2.7, 2.8, and 3.1 are due November 10th at 11:59 p.m. People get confused when I use the 24-hour clock, so I'm trying. 11:59 p.m. Also remember, you've got assignments due tonight, right? And where are they? Well, they are in week 7, because that's when we did it. So all those 2.1, 2.2, 3, 4, 5, 6, those are all due tonight at midnight. They're itty bitty for the most part. 2.1 I think is the biggest one, and then the rest of them are just really small. So doesn't mean to put it off, but now might be, or today might be a good day to tackle these. Okay, so we're going to keep going with these quadratic functions. We're going to do 23 from last day. So I think we did 14. Okay. So from here, we did 14. I want to do 23 today as kind of a review slash getting started one. In fact, oh, copy. There. So we'll do 23 today for review. And then the rest of that section we've already talked about, but we'll talk about it just briefly. So 23, what we have to do, remember, is we've been given a quadratic function, sure enough, x squared and an x and a constant, looks like a quadratic to me. We have to express this in standard form. What we found last day is this is probably the hardest part of these questions. After we have it in standard form, we can find the vertex, the x and the y-intercepts. Remember, the x-intercept is where y is 0 and the y-intercept is where x is 0. We have to keep those in mind. Then we're going to sketch the graph and we're going to find the domain and range of this thing from the graph. Okay. Just as a heads up, for quadratics, the domain will always be the set of real numbers, so from negative infinity to positive infinity. Okay. So let's see here, we've got f of x is negative 4x squared minus 12x plus 1. Okay. So putting this thing into, oh, not there, into standard form, we have to remember how to complete the square. So I'm going to bring this guy in here too and just put it here because let's see if I can clean it up a little bit. Okay, so we have to remember how to complete the square. And so what we do is we have to write this thing so that we can just talk about x squared plus bx. So not ax squared plus bx, but just x squared plus bx, which means I have to pull this negative 4, which is my a, outside, right? Which means I'm going to try to factor out a negative 4 from this negative 12. Luckily, it looks good. It looks like I can. So, and then I'm going to add b over 2 squared. But then I'm also going to subtract b over 2 squared because I can't add and just without subtracting. That means I'm changing the function. What are some things we notice right away? Right away, we see that this thing is negative, right? So a is negative 4. Let's just make a note here. A is negative 4, which is less than 0. So the parabola is pointing down, right? That's what we know. So the parabola is pointing down. If it's pointing down, that means the vertex is a maximum, right? So let's make a note of that just so we can keep that in mind. So therefore, the vertex is a maximum, right? So these are things that we know without doing any work, right? We know that this vertex, whenever I find it, is going to be a maximum. Okay, so I first need to get this thing into standard form, I first need to factor out that negative 4. So part A, standard form. So I'll start here at f of x is negative 4x squared minus 12x plus 1. I'll just make sure, good. Factor out that negative 4. Negative 4 times x squared plus 3x, and then plus 1. Notice that I just want that x squared plus bx, so 3x in this case, because this is what I need to make a perfect square, x squared plus bx. So now I can use this to make a perfect square. make a perfect square. Okay. So we're going to focus our attention in here, x squared plus 3x. So what completing the square says that x squared plus bx, and then if I add b over 2 squared, then I can rewrite this as x plus b over 2 all squared, right? A perfect square. So what that's going to look like is I'm going to have minus 4 times x squared plus 3x, and then I'll use a different color for when I'm completing the square here, plus b over 2 squared, 3 over 2 squared. Okay, so b is 3, positive 3, b over 2, and then squared is 3 over 2, then squared. But if I'm adding it, I also have to subtract it, so minus 3 over 2 squared. And then outside these brackets, plus 1. Don't forget about that plus 1. Okay. Here, completing the square by adding 0, right? Notice that whatever this 3 over 2 squared is, and then I'm subtracting that same amount, so I'm adding 0, right? But what I'm going to do now is I'm going to regroup things, okay? And this is going to become a perfect square, right? So here, what I can do is I get negative 4 times x squared plus 3x plus 3 over 2 squared. Okay. I'm going to block that off. In fact, maybe I'll use bigger brackets here. But then notice that this negative 4 is also multiplying this last term in here, right? So if I'm breaking out these brackets, then I still have to make sure that this multiplies over here, right? And so what I get is I get plus negative 4 times negative 3 over 2, oh sorry, minus 3 over 2 squared, and then plus 1. Only because it's, so minus 3 over 2 squared times negative 4. So it's going to be positive. All right. So this whole thing I can rewrite as a perfect square. So this is perfect square. So now I can rewrite that as negative 4 times, and let's just remember, okay, so if we've got x squared plus bx plus b over 2 squared, we can rewrite that as x plus b over 2 all squared. So what we have is x plus 3 over 2 all squared. So we'll replace those with x plus 3 over 2 all squared, and I'll do big brackets here. Okay. Then I've got minus negative 4 times 3 squared over 2 squared, right? I can expand this square inside. And so I've got plus 4 times 3 squared, so that's 9 over 4, plus 1. Well, 4 over 4 is going to cancel, so I have plus 9 plus 1. So this becomes negative 4 times x plus 3 over 2 squared plus 10, 9 plus 1. Okay, So comparing this with our standard form, okay, compare with standard form, which was f of x is a times x minus h. Where did we have it? X minus h squared plus k. Okay. Making the connection here between, so a is -4, we already established that, so that's good that it stayed that way. X is here, h, so -h is 3/2, which means h itself is -3/2, and then k is going to be 10. So, oops, h is -3/2, and k is 10. Okay. So that was part A, was finding f in standard form, so that's what we've done. Part B, find the vertex and x and y intercepts, so let's go ahead and do that. Now we're on easy street, right? Finding the standard form is the hard part. Part B, the vertex is at hk, which in this case is at -3/2, 10. The x-intercepts, remember the x-intercepts are where y equals 0. So let's just do a little graph here. The x-intercepts here are where y equals 0, and the y-intercept is where x is 0, right? So just keeping in mind, okay, the x-intercepts are where it crosses the x-axis, which is where y is 0, and the y-intercept is where it crosses the y-axis, so that's where x is 0, right? Here's 0. So the x-intercepts, we'll start there. Bump this down a little bit. Just as a reminder, this is where y equals 0. Okay. Here, I'm going to use the standard form. It's a little bit, I find it easier to deal with because I don't have to use the quadratic formula, but you totally can if you want to use just the general form. So it doesn't matter which form of this quadratic you use, you'll get the same result. So what we do is we remind ourselves that f of x is -4 times x plus 3/2 then squared plus 10. So if y is equal to 0, then we set f of x equal to 0, f of x is equal to y. -4 times x plus 3/2 squared plus 10. And then I just go ahead and I solve for x. Typically, there's going to be 2 solutions, right? If there are any solutions, there should be 2, because remember a parabola, if it's above the x-axis, it's going to cross the x-axis at 2 points, right? If it's below the x-axis and it's pointing down, then it won't cross the x-axis ever, so you won't find any solutions. Typically that kind of rears its head by taking the square root of a negative, which we can't do. So that's one surefire way of knowing we don't have any x-intercepts. Here, knowing that the vertex is at x is -3/2, so I'm moving over a little bit, and then when y is 10, so I'm up above the x-axis over to the negative side a little bit. And then I'm pointing down, so I am expecting to see some x-intercepts. So let's see what they are. But that's one thing that you could check. You could check your vertex, if it's up or down, right? All right, so solving for x here, I have to subtract 10 from both sides. So negative 10 is negative 4 times x plus 3 over 2 squared. I have to divide both sides by negative 4. So I get negative 10 divided by negative 4 is x plus 3 over 2 squared. Negative 10 over negative 4 is, of course, just 10 over 4. And in the same breath, I'm going to take the square root of both sides. When I take the square root, though, I have to remember that the square root actually yields the positive and the negative version of itself. And so here, this becomes the plus minus square root of 10 over 4. That's a good thing, right? Because that's how we end up with two different values for our x-intercepts. We know it has to cross the x-axis at 2 points. Is equal to x plus 3 over 2. Okay. You could just as easily have found these exact same values by using the quadratic formula, totally fine, from the general form. So x here is going to be plus minus the root of 10 over 4 and then minus 3 over 2. Okay. This is the exact form, just as a heads up. I don't see it making any nicer values than that. I guess I could find, I have a common denominator of 2, right? Root 10 over root 4 is root 10 over 2. I could simplify it a little bit, I guess. Sure. I guess. If you left it like this, that's totally fine. I'm okay with you calling that your exact form. So x is going to be root 10 minus 3 over 2. Oh, plus minus. Okay. Roughly though, because it's hard to know where that is on the x-axis, right? Roughly, so the approximate result is going to be root 10. So I'll do this positive side first. So root 10 and then minus 3. Make sure your minus 3 is not under the square root. Minus 3. And then divide that by 2. I get roughly 0.0811388. And for the negative root 10, kind of step it out if you're using a calculator like this, minus 3 divided by 2 puts me at roughly negative 3.08811,388. Okay. So those are approximations. It's a little bit easier to think about on the x-axis, right? So I've actually got those reversed, but that's okay. Y-intercept is a little bit easier. That's where x is 0. So if we've got our original, I'm going to use standard form. Doesn't matter, you can use the general form. All you're doing is plugging in 0 for x and solving for f of x. So I'm just going to cheat and copy, paste. Okay. So now I'm plugging in x is 0 here and solving for f of x. That's negative 4 times 0 plus 3 over 2 squared plus 10. And so 3 over 2 squared and then square that, times -4, and then plus 10 puts me at 1. Wah, wah. Okay. So far, right, I found the X and the Y-intercepts, especially approximations of the X-intercepts, but that's okay. That's good for graphing. So now what do we have to do? So find the vertex and the X and Y-intercepts of F. Oh, it's still catching up, sorry. Then we're gonna sketch the graph of F, okay? I'm gonna confirm it using Desmos, of course. I wanna make sure that I did everything correctly. And then we're gonna find the domain and range. So part C is sketch a graph. Sketch this thing. So first thing I'm gonna do is I'm gonna start with my vertex, right? And then I know it's pointing down, so that's really helpful. So let's see here, -3/2 is -1.5 and 10. So here I might put it somewhere up here, -3/2 and 10. Okay, this is a sketch, so I'm not going to bother with all my nitpicky axes here. I know my y-intercept is at 0, 1. Okay. And then my x-intercepts are at positive 0.08 and -3.08. So probably somewhere here. 0.08 0, and maybe here -3.08 and 0. Okay. I can go ahead and sketch this thing by connecting these dots, keeping in mind a parabola has a nice kind of bowed shape, right? I don't want to see straight lines because that's the absolute value function, so that's a little bit different, or that's really different. So I want to see kind of a curve, and that's hard to do, I know, but I know what I'll do. Oopsies, wrong color. I'll just move this 0, 1 up a little bit to match my curve. Looks like I'm gonna have to kind of move this out a little bit, but that's okay. It's just a sketch. Oops. It's because it's not to scale, all right? Not to scale. Okay. That's okay. It gives us a good idea of what this thing looks like. And so now we're going to confirm using Desmos, confirm your work using Desmos. And then because I always forget to do the domain and range, I'm going to put them down here. The domain and the range. The domain, we can look at our sketch, even though it's not beautiful, it still works, right? So the domain is going to be the set of real numbers, because remember parabolas, they actually keep going and going and going and going until positive and negative infinity. So even though it doesn't look like it, on the x-axis, they spread out to infinity. So the domain here is always going to be the set of real numbers, or from negative infinity to positive infinity. The range, in this case, the range is the same thing as the domain, but on the y-axis, right? And so it looks like it goes from negative infinity, and then it stops abruptly at 10, y equals 10. It goes up to 10, but not past 10. And so the range is from negative infinity to 10, including 10. So we can do all of these with just our sketch, and Desmos is really just to check our work. So here we go. So what I'm gonna do first is I'm gonna check that my standard form is correct, that my standard form gives me the same graph as the general form. So where are we here? All right. So we'll start with the general form, which was negative 4x squared minus 12x plus 1. Okay, looks good. In fact, if I just click here, looks like I'm getting the same values that I was finding. So that's really positive. Okay, and my standard form was negative 4 times x plus 3 divided by 2. Make sure your 3 over 2 actually looks like the way you expect it to, so your x isn't divided by 2 as well. And put a bracket on, square that, and then plus 10. All of a sudden, you have the same graph. So this confirms a lot of my work, right? Or all of my work, actually. It confirms that my standard form that I found is the same graph, so that's good. It confirms that the vertex is at negative 1.5, so 3 over 2, and 10. It confirms my y-intercept is at 0, 1, good. My x-intercepts are at negative 3.081 and 0.081, which is what we found. Desmos likes to give approximations just because on a number line, approximations make more sense. Okay. Great. So that's how we confirm our work using Desmos. It's always nice to know that you're on the right track. And I really, really want you to check your work using Desmos. There's no reason for any of these questions to be wrong that you're submitting, right? And so, because you can always check your work. I'll be checking to make sure that you've done the work algebraically, but you can check your work by yourself, right? To make sure you're not mucking it up. Okay, so the last little bit of this section is really just more on what we've been talking about, right? And so here, right, we said, okay, well, if A is larger than 0, so if A is positive, then this minimum value is the vertex. Okay, so here, let's copy this in. Okay. So what we're saying here is that once we have the standard form, then we know the vertex is at hk, and so f of h is equal to k. Well, that's just the vertex, right? And so all it's saying is that, well, if you have the vertex and A is positive, then it's pointing up, then that vertex is a minimum. And if it's pointing down, so A is negative, then you have a maximum. So nothing crazy there. We've also got this note that you could go from the general form. I'm going to leave these here. I'm not going to bring these in because I want you to just move into the standard form. So this one I find is a little bit more confusing. Of course, what you'll find is if you went ahead and did it, if you went from the general form of this ax squared plus bx plus c, you completed the square, you did everything, what you would find is that negative b over 2a is going to be the same as h. Okay, it's going to take some work because you'd have to work with this general form and put it into standard form, but that's all it's saying. We're not going to go into that. And I think I'll leave these as exercises. I want you to focus on just being able to graph quadratic functions. Okay? The rest will kind of follow. Okay. So 3.2, I'm keeping an eye on the chat, but so far it's just Nick saying good morning, which is nice. But if you do have questions, let me know either in the chat or just turn your microphone on, that's fine too. But otherwise, let's keep going. So in those notes that I posted on Moodle, you've got polynomial and rational functions part 2. So I just split up the notes from last day. And I simplified the notes from 3.6, it's called rational functions. I made them a little bit shorter, so you might want to check that out if you have the notes that I posted last day. But, all right, so polynomial functions and their graphs. I'm going to focus on graphing quadratics, and then we're also going to graph rational functions. So polynomial functions, we're not going to graph that much. So we're just going to kind of breeze through this section. Here, polynomial functions and their graphs. I'm trying to remember what it's called. Polynomial functions and their graphs. Okay. So we've got a couple of takeaway messages, but here what I'll just kind of say is we will focus our graphing on quadratic functions like we just did. In the previous section. And rational functions which we'll call 3.6. It's at the end of the notes. So here, even though we'll talk about some of the graphs, it's not something that I want you to focus too much on, so we're not going to spend a lot of time here. But it is good to kind of develop some terminology about polynomials in general, even though I feel like we've talked about, here, let me see if I can grab. Okay. So polynomials have degrees, right? And so a polynomial in general is just if you've got x's to different powers, they can have coefficients. So each is allowed to have a coefficient. And then we usually write them in decreasing powers. So x to the power of n, x to the n minus 1, x to the n minus 2, all the way up to x to the power of 1, right? And then technically x to the power of 0. Anything to the power of 0 is just 1, right? So just remember that. Where of course a subscript n, so the coefficient of the first term can't be 0 because then the degree is not n anymore, it's n minus 1. So these a's in front are called coefficients, right? The a subscript 0 is the special case where it's the constant coefficient because it's just going to be a constant. Of course, a quadratic function is a polynomial, degree 2, right? So here, a quadratic f of x is ax squared plus bx plus c is a polynomial degree 2. So here, we're just expanding our knowledge about, so from the quadratic, we're going to move to any degree polynomial. Okay. So this first here, a, or a subscript n, so it's allowed to be attached to any x to the power of whatever the degree is called the leading coefficient. Okay? And it dictates the kind of the shape of this thing, if it's positive or negative in the quadratic sense, and then we'll talk about odd and even polynomials. Okay, and then this guy here is your leading term. Okay, so the leading term determines the general shape of the graph. So what does that look like? Oops. The end behavior is what I call the general shape of the graph. Okay, so here, let's make this nice and big so we can talk about it. So if we have some polynomial, so any polynomial with a leading term, a subscript n, x to the power of n, it's determined by the degree of this thing, so what n is, okay, and the sign of the leading coefficient, a to the n, or a subscript n. So if this polynomial, which we typically denote by p of x instead of f of x, just to highlight that it's a polynomial, not just any function, it's a special function polynomial. If p has an odd degree, so x to the power of 3, x to the power of 5, x to the power of 15, right? If we have an odd degree, what we said before when I said, okay, remember these functions, x to the power of 3, right? So recall, x to the power of 3, we said had a shape kind of like this, right? So notice, if this polynomial has an odd degree, x to the power of 3, for example, then the end behavior is still going to have that same shape, right? So here, this here is the end behavior. So we only need to remember what x to the power of 3 looks like, and then we know that any odd degree is going to have that same sort of end behavior. And we've already talked about this. Anything can happen in here depending on, you know, how many terms you have affecting the graph. But the end behavior is only going to be determined by that degree of the polynomial. And the other option is, if you have an and a is positive, okay, so the leading coefficient is positive, then it behaves the same way, okay? But if you have a leading coefficient that's negative, then what does that look like? Well, then you have negative x to the 3, so things just turn around, okay? And negative x to the 3, in general, is going to be the opposite, but the end behavior looks like this. Oops. Okay. We've talked a lot about polynomials in the last section, right? So that we know if the leading coefficient is positive, well, then we know how it's going to behave. It's going to be some sort of parabola-esque thing pointing up. What happens when you have a higher degree than 2 is that you get some activity here. So if you have a degree 4, for example, you might have some activity here in the middle, but the end behavior, if the leading coefficient is positive, is that it's pointing up, right? So both arms are pointing up. And if the leading coefficient is negative, then they're pointing down, just like we saw before, right? So these are important to keep track of, right? Just to have a general idea of what this thing looks like, remembering that we can't possibly know what's going on in here. There are ways, but we're not going to get into that, not in this course. So just use Desmos for the midsections, right? You can even use Desmos to make sure that you've got the right end behavior. because that's something that I might ask you, right? So what's the end behavior of this thing? What do you expect it to look like? Yeah. So let's talk about here. The end behavior of a polynomial, right, is a description of what happens when x becomes large. So as x goes to positive infinity, so if we have an odd degree and the leading coefficient is positive, then as x goes to positive infinity, y is going to go to also positive infinity, right? Where f of x is going to go to positive infinity. So as x goes to negative infinity here, right, then y, or the output, f of x, is going to go to negative infinity in this case, right? So that's what we have here, right? As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity, right? As opposed to the even degrees, and if it's a positive leading coefficient, then as x goes to negative infinity, so as you move your way out here, then y is going to positive infinity. As x is going to positive infinity, y is also going to positive infinity. So that's how we describe these things. So we use these to describe our end behaviors, right? That type of notation. See box above for full end behavior descriptions. Okay. So these don't really play a role yet. They're going to come back to haunt us, so I'll just bring them in and we can talk about them just briefly. But the key thing is that these are all saying the same thing. Okay. So if P is a polynomial and C is some real number, so lowercase c is a real number, then the following are equivalent, right? So, and we've already used some of these facts. We haven't talked about it explicitly, but what we said is that, okay, if C is a zero of P, a zero meaning it's an X-intercept. Zero is an X-intercept. X equals C is a solution of the equation P of X equals 0. Well, that's an X-intercept, right? Where the function is equal to 0, so where y equals 0, that's the X-intercept. Okay? So then X minus C is a factor of P of X. That's the fact that we used when we used the quadratic formula to figure out how to factor quadratics, right? Then we said, okay, well, if C is a 0, right, then X minus C must be a factor of P of X. So we've already used these, just not explicitly. And then, of course, C is an X-intercept of the graph of P, which is what we established up here, but not in the same words, right? So here, all of these things are essentially just saying this is where this thing crosses the x-axis. Okay. The intermediate value theorem is kind of a funny theorem. It's pretty obvious, but it comes up later in calculus if you go down that route. But just keep in mind, so the intermediate value theorem says that if you have a polynomial, then if P of A is negative and P of B is positive, then at some point between A and B, this thing had to cross the x-axis, so at some point C, it's equal to 0. That feels kind of obvious, right? But just remember that that's a thing, so it's called the intermediate value theorem. And so all it requires is that P of A and P of B have opposite signs, and then at some point, it would have crossed the x-axis, going from positive to negative, for example. And so at some point C between A and B, it's equal to 0. So just kind of good to know. Okay, so I've included the guidelines for graphing polynomials, right? We've used test points before to figure out where things are positive and where things are negative. So we've actually already worked through a lot of these. But now we incorporate the end behavior. And like I said, I'm not going to focus on graphing polynomials, right? But the guidelines are here, and that's good. So let's keep that in mind. I don't really want to do this. What I want to do, okay, fine. Fine. We will focus on graphing quadratics and rational functions. Okay, so these are just kind of good to know. But not really needed for us. Okay, we're gonna graph some tough stuff, so so I don't wanna spend any more time on this, but what you would have to do is you would find the zeros of this thing, so that's what we were doing when we found the X-intercepts, and then you make some test points, so you factor this thing out and you figure out where it crosses the x-axis, and then just like we were doing before, I can't remember where we were doing it before, but we've actually done this. We have done this in chapter 1 somewhere. Oh, in inequalities. We didn't graph them, but we figured out where they're positive and negative, meaning where are they above the x-axis and where are they below x-axis, or the x-axis. All right, and then we need to know the end behavior, so that's the one takeaway from this section that I want you to have a good handle on is, okay, the leading coefficient determines if it's positive or negative, right? And then if it's odd or even, that determines the end behavior, right? So here, this is the takeaway from this section. And remember the end behaviors. Just to complete our notes here, I'll bring this whole chunk in. Oh, now I've done it, haven't I? Ran out of room. All right, whatever. So we have some sort of factor, so x minus c and x minus c to the power of m, then we say it's multiplicity m. Okay, so because c is a 0, crosses the x-axis at c, right? But then it's to the power of m. So then we say that c is a 0 of multiplicity m. And depending on the multiplicity of m, right, if m is odd, so x minus 4 to the power of 3, for example, right, then depending on what the leading coefficient is, right, then you would have, okay, so m is odd, which means you're going to have this type of shape. Let's say the leading coefficient is positive, then you would have this type of shape. And so that means that it's going to cross the x-axis. Whereas if m is even, then you're going to have this kind of parabolic shape. And depending on if it's positive or negative, right, it's going to be either at c as a minimum here or as a maximum here. It just depends on what's going on. And then just as a little blurb, because now I've got space. In fact, why not put it here? If you have a polynomial, okay, the local extrema, so these are minimums and maximums. Remember, you can have more than one minimum or maximum. And so the local extrema of polynomials, so if you have a general polynomial degree n, then the graph of P has at most n minus 1 local extrema. So if you have a degree 3 polynomial, then you know that you can only have 3 minus 1 local extrema. So you can only have 2 mins or maxes. Okay? But that's just extra. Okay. Okay. So I'll leave these just kind of as an exercise. You don't have to spend that much time on them, but maybe try one or two and see how it goes. All right, so what I really wanted to get to today, because it can be a little bit tricky, and it is really important, is dividing polynomials. So here, where are we? I want a new page. That page. So 3.3, it's called, is called dividing polynomials. We're going to use long division, which is weird, right? But we're going to go through quite a few of these, and hopefully you'll see the pattern and you'll just be able to do it. So why would we want to be able to divide polynomials? One example would be if I need to extract a factor, right? If I need to force out a factor of x minus 4, for example, then using long division, I can do that, right? So here, this will give us the tools to force out a factor from a polynomial. Okay. So before we can do any long division here, oh, let's bring all, no, let's bring just this in. Okay. There's some terminology that we need to establish first. Okay, so if P of x and D of x are polynomials, as long as d of x is not equal to 0, because it's going to be the divisor, so we can't divide by 0. Then there exist unique polynomials q of x and r of x, where r of x is the remainder is either 0 or of a degree less than the degree of the divisor. So we can rewrite p of x over d of x. So this is a polynomial over a polynomial, right? Is equal to q of x, which is the quotient, plus the remainder of x over the divisor. Or you can rewrite it depending on what makes it easier for you to work with, right? Or you can write p of x, which is the original dividend, dividend, I want to say dividend, which is going to be d of x, which is the divisor, right, times the quotient q of x plus the remainder r of x. Okay. Notice that these two, this is a polynomial over a polynomial. Okay. So we're going to be able to pull out a factor d of x here, and we can rewrite it as d of x times q of x plus r of x. Okay. There are two ways that we could do this division. They're very similar. I'm only going to show you one, the one that I prefer. The notes, of course, have both. So there's long division or synthetic division. I actually find synthetic division, even though it's supposed to be easier, I actually don't like it. It's, I don't know, it's not as intuitive to me. So the long division, that's the one I'm going to stick with, but you can have a look at the synthetic division, and if you prefer that way, that's totally fine, and you can use that way, but I'm going to stick with just long division so we're not clouding our brains with too many options to do the same thing. And it's usually a good thing, but sometimes it can get a little bit tricky. So there are two ways of dividing, that's what I should say, of dividing polynomials. The first one is long division. And I'll say, we will use this. And the second one is synthetic division. And I'll just say outlined in the notes. Right, feel free to use it, but we're just going to work through the long division and really figure out how to do that. So, how do we do long division? Well, it might have been a long time ago, or if you're like me, you got through all your schooling without ever doing long division. Isn't that crazy? I skipped grade 6, I guess that's where you cover long division, and because we moved back and forth between Sweden and Canada, so I didn't learn long division, and I still managed to get a math degree in university. So long division, I understand if you haven't done it in a long time or possibly even ever. So so we're going to take it nice and slow here. Long division. So long division is probably easiest if we just show by example. So, oops, combining my words again. Long division of polynomials by example. So let's say I have 6x squared minus 26x plus 12, and I want to divide that by x minus 4. You can see how this would be useful, because if I want to pull out an x minus 4 from here, right, if I need an x minus 4, this is a surefire way that I'll be able to do that, right? So if I pull out an x minus 4 from here, I might be able to factor it more easily. Okay? It could make a mess, but sometimes it's helpful. Okay, so here, let's just establish some terminology. So here, this is p of x over d of x, where p of x is the dividend. Oops. Dividend over the divisor. Okay. What this thing becomes is p of x over d of x is going to give us q of x plus r of x over d of x. Q of x is the quotient, and r of x is the remainder, which might sound familiar. Okay, so the first step you're going to take is you're going to rewrite this as if you're doing long division, right? So remember, you've got that kind of curved bracket with the sort of square root looking divisor thing going on. So here, let's see here. Maybe I'll use step 1. Rewrite p of x over d of x as d of x divided into p of x. Okay, so in this case, I'm going to rewrite this thing as x minus 4 going into 6x squared minus 26x plus 12. So I have, I'll use a different color, x minus 4 divided by, and what was it, 6x squared minus 26x plus 12. Okay, so here I've rewritten it, and that's my first step. Okay. Next thing I'm going to do is I'm going to take this term, right, the leading term it's called, leading term, oh, actually 6x squared, this whole thing is the leading term. Okay. Step 2 is to divide the leading terms. Divide leading terms. Put the result up top, if that makes sense. Put the result, oops, up top. So what do we have? We have x minus 4 going into 6x squared minus 26x plus 12. Okay. So now I've got a leading term of x and a leading term of 6x squared. So I'm going to do 6x squared divided by x. Okay, just on the side here. 6x squared divided by x makes 6x, right? And so that's what's going to go here, 6x. Now, okay, now I have to multiply this guy down by the divisor, okay? So then step 3 is multiply the result by the divisor and place below the dividend. You can see how we needed that terminology. Okay, so what that's going to look like is you're going to take 6x times x, that makes 6x squared, and then 6x times -4 makes -24x. Okay. So here we are, x minus 4 going into 6x squared minus 26x plus 12. I've got 6x here. Down here, I'm going to have 6x times x minus 4 becomes 6x squared minus 24x. Okay. That's going to go here. In fact, not that far. So now I have 6x squared minus 24x. Okay. What I do now, right, is you've got a couple of options here. You could bring this plus 12 down to kind of complete it. I'm going to leave it there for just a little bit. Now, making sure that you subtract both of these. So your next step is to subtract the result, let's call it, so this thing from the original. Okay. So step 4, subtract the results from the dividend. Okay. So what we get is we get x minus 4 going into 6x squared minus 26x plus 12. Don't forget, you already have that 6x up there. And that's how you ended up with 6x squared minus 24x. Oops. So now, it's a different color here. You have to subtract this from here. Notice what's always going to happen is that these terms are going to go away, and that's how you've reduced the thing that you have to divide by x minus 4, and so that's how you're going to chip away at this thing. And so we get 6x squared minus 6x squared puts us at 0. Okay, that's always going to be the case. Making sure that you bring this negative inside, so you get negative 26x plus 24x. Notice that these x's and x's should be lining up, right? It's possible you might have to make little holes, right? If we were only dividing 6x squared plus 12, you would have plus 0x here, so you'd have to make room, but this is just the beginning, so we're just gonna start here. Negative 26 plus 24 puts me at negative 2x, and then technically minus 0, so 12 minus 0 puts us at plus 12. Okay. Now, we can consider this our new dividend, right? Kind of temporary new dividend. I'm going to use that to make my step 5. So now I do the exact same thing, right, that I just did with this new dividend. And repeat the procedure with the temporary new dividend. until, okay, so we keep going until the new dividend is kind of smaller than the leading term, right? So there's no more x's that I could divide by. You could be doing by x squared, so that's why I don't want to say just x's. But you keep going until the new dividend has a lesser degree. Oops, hey, what happened? Lesser degree than the divisor. Okay. So let's see what we've got here. I'm going to write this all out here. In fact, it doesn't hurt to kind of go through this again. X minus 4 going into 6x squared minus 26x plus 12. Okay. 6x squared divided by x puts me at 6x here. 6x times x minus 4, so that puts us at 6x squared. 6x times negative 4, negative 24x. Subtracting these guys, I get 0. Negative 26 plus 24, negative 2x plus 12, right? Technically minus 12 minus 0 plus 12, so that's what brings it down. Now I do the same thing. I take negative 2x divided by x. So here, negative 2x divided by x is negative 2. So that's what goes here. Okay. Now I do the same thing and I multiply negative 2 by x minus 4, and that's what goes over here. So now I do negative 2 times x minus 4 puts me at negative 2x plus 8. So that's what's going to go here. Negative 2x plus 8. Then I'm going to subtract this, right? Putting brackets all around this here. So now I get negative 2x plus 2x. Again, that if it doesn't go to 0, you've done something wrong. So something is kind of missing, or you forgot to subtract, or something like that. So that would be a kind of a check-in point. And then 12 minus 8 puts me at plus 4. This is the end of the road, right? Because I don't have an x to divide by x anymore, right? And so here we're finished. And so what we found is that the remainder is 4. Okay. The quotient that we found is this whole thing. Okay. So what we found is that q of x is 6x minus 2, and r of x is the remainder, which is 4. Okay. So there are two ways that we can rewrite this, this result. And remember, p of x, oops, p of x was 6x squared minus 26x plus 12. And d of x, oops, was x minus 4. So we can rewrite this answer, right? P of x over d of x. We can write the result in two different ways. Right, the first one is that P of X over D of X is equal to Q of X. So this is just from that note way back here. All right, we can write it as Q of X plus R of X over D of X, or P of X is D of X times Q of X plus R of X. So we're just going to rewrite these answers in those two forms, but they're equivalent. Just depends on what makes your life easier. Q of X plus R of X over D of X. So in this case, what would that mean? It means that 6x squared minus 26x plus 12 divided by x minus 4 is Q of X, 6x minus 2, plus R of X, which is 4, over D of X, x minus 4, plus 4 over x minus 4. Notice that we don't have a common denominator here, right? But if we wanted to, we could find the common denominator of x minus 4, or force the common denominator of x minus 4. Or we can write it in the second option, which is P of X equals D of X times Q of X plus R of X. This is just forcing the common denominator and multiplying it over, right? So then we would say that 6x squared minus 26x plus 12 is D of X, which is x minus 4, times Q of X, which is 6x minus 2, plus the remainder, which is 4. This especially can be helpful for factoring, right? Or even this. So sometimes you can factor using this. It's a little bit hard, but and not something that I'm gonna get you to do, but we are gonna use, I'm just gonna kind of grill you on how to do long division of polynomials so that you know it and have it. Okay, so before we do any more examples, and we will do lots of examples, or a couple of examples, I should say, let's talk about the factor and the remainder theorems, because they're not that complicated. So, and they're not that far-fetched, but while it's fresh. Okay, so like I said, the note's gonna go through our long division. This is the exact same example, but of course, I wanted to talk you through it. Same thing with the long division. You can have a look, but you don't have to. Here, we're gonna work through some of these problems in a little bit here. But first thing I wanna do is talk about the remainder theorem, okay? For some reason, the remainder theorem and the factor theorem are on your learning outcomes. So here we are, we have to do long division to get here. But once we've done the long division, it's actually not that crazy at all. So what it says is that if a polynomial P of X, right, is divided by X minus C, so notice that this is a special form of the divisor, X minus C. In fact, we had X minus C here. We had X minus 4, so C in our case would be 4. Then the remainder, okay, our remainder over here was 4, which can be confusing, right? X minus 4 and the remainder is 4, they're completely separate. Then the remainder is the value of the polynomial, original polynomial evaluated at C, okay? So from our previous example, okay, P of X was 6x squared minus 26x plus 12, okay, was divided by x minus 4, which tells me that c is equal to 4, okay, to match here. So it's divided by x minus c, it's divided by x minus 4, so c in this case is 4. We found a remainder. We found the remainder to be r of x is equal to 4, right? We found r of x, the remainder is 4. Okay. The remainder, so what the remainder theorem says is that, well, if the remainder that we found is 4, then the original polynomial evaluated at c, which happens to be the same number, so we're going to come back to this with different numbers. So the original function evaluated at c equals 4 is going to be 4. We can confirm this, right, by plugging x equals 4 into our original equation. But so we found the remainder to be r of x is equal to 4. Therefore, by the remainder theorem, p of x equal to c equals 4 is equal to r of x here. Put it down here, is equal to r of x, which is equal to 4. Confusing because they're both equal to 4. So that's why I wanted to have these things. So we can rewrite this as p of c is equal to r of x is the remainder theorem. Okay. So we can check this. If we plug x equals 4, or sorry, x equals 4 into here at 6x squared minus 2x plus 12, we should get a result of 4, confusingly enough. Check. P of 4 is going to be 6 times 4 squared minus 26 times 4 plus 12. 6 times 4 squared, so 4 squared is 16 times 6 is 96. Minus 26 times 4 minus 104 plus 12. 96 minus 104 plus 12 puts me at 4, which is the remainder. We're going to check that again, but with different numbers. Okay. The factor theorem, let's just throw it on here for completeness sake. Actually, let's include all of it. We already said this, right? C is a 0 of p if and only if x minus c is a factor of p of x. So if you get no remainder, then x minus c is a factor. If we find r of x minus is equal to 0, right? So the remainder is 0, x minus c is a factor of p of x, right? Which kind of goes without saying. So that one, not that complicated. All right, let's do an example where the c and the remainder aren't the same, potentially. I haven't gone through these yet, so who knows? We'll do some of these. Okay. let's do 4 to start. Okay. So 4 says P of x is 3x to the 3 plus 9x squared minus 5x minus 1. And d of x is x plus 4. Notice that it's x plus 4. The factor and the remainder theorems that we talked about, we're talking about x minus c. So in this case, the c would be -4, right? X minus -4. X minus -4. Therefore, c is equal to -4. Okay, so just as a heads up. But that's all right, doesn't matter. All right, so what we're going to do is we're going to use long division to divide these, and then we're going to write them out in 2 different ways, just like we did up here, right? We can either write it like this, or we can write it like this. You'll notice that they're the exact same. All right, long division. Without the steps, here we go. X plus 4 is going into 3x to the power of 3 plus 9x squared minus 5x minus 1. Okay. Taking it nice and slow, I take my leading term and divide it by the leading term, or this leading term rather, 3x to the 3 divided by this leading term, which is x. So just on the side in kind of a dream bubble, I guess, I have 3x to the 3 over x, which is going to be 3x squared. So that's what goes here, 3x squared. Next thing I have to do is I have to multiply this down, right? 3x squared times x plus 4, and I write it down here below, right? And so here I'll just kind of number my steps in colors. And so my second step is to take 3x squared times x plus 4, which is going to be 3x to the 3 plus 12x squared, which goes here. 3x to the 3 plus 12x squared. You obviously don't need to show these side pieces. I'm just doing them so you can see what's going on. Next step, I guess, e squared. Next thing I have to do is I have to subtract here. Notice that I should end up with 0 here, so 3x to the 3 minus 3x to the 3, phew. 9x squared minus 12x squared, right, is going to be negative 3x squared. Let me just make sure brain's not, it should be negative 3x squared. Okay. Negative 5x minus 0 is negative 5x, minus 1 minus 0, minus 5x minus 1. So if you want to think about them just dropping down, that's fine. Or if you want to justify it by saying minus 0, either way you're doing the same thing. Okay, so let's see here. Now I do the same thing with negative 3x squared. Negative 3x squared divided by x. So here, my fourth step is negative 3x squared divided by x is negative 3x. And so negative 3x goes up here. Negative 3x times x plus 4. So again, I'm back over here. Negative 3x times x plus 4 is negative 3x squared minus 12x, which is going to go here. negative 3x squared, oops, not under those, but under the x squared, negative 3x squared minus 12x. And then my sixth step is to divide these things, or sorry, subtract. We're dividing this whole time. Negative 3x plus 3x, or x squared, I guess, 0. Negative 5x plus 12x, negative 5 plus 12 is 7. So plus 7x minus 1. Okay. I want you to use your calculator. Things can go so wrong, even if it's something that you're really, really sure about. Just double check it with your calculator. So I don't want you to feel like there's any shame in using your calculator. There isn't. Because if this value is wrong, then your whole thing is going to fall apart, and then you have to start all over again. It's just a mess. So the next thing we're going to do, right, I've still got an x, so I can divide x into it again, right? So here, now we're back. The sixth step is going to be to take 7x divided by, oops, x is just 7. Which is going to go here, plus 7. Then I take the 7 times x minus, or x plus 4. So the seventh step is 7 times x plus 4, which puts me at 7x, 7 times 4, plus 28. Just be careful, which is going to go here. So I get 7x plus 28, which in my 8th step, I'm going to subtract. So I get 7x, oops, forget my subtraction here. 7x minus 7x is 0. Negative 1 minus 28, negative 29. Okay, we did it. It's a lot of back and forth, right? But you're doing the same 3 steps over and over again until you run out of x's to divide by. And then you're done, right? So now we know your q of x. Actually, let's say, therefore q of x, I already had p of x and d of x, is 3x squared minus 3x plus 7. R of x is negative 29. Okay. So we can write first p of x over d of x is equal to q of x. Once you have q of x and r of x and p of x and d of x are from the question, writing these out the different ways is not hard, right? You just plug in what you found, plus r of x over d of x. So in our case, p of x is 3x to the 3 plus 9x squared minus 5x minus 1 divided by x plus 4 is equal to q of x, which we found was 3x squared minus 3x plus 7 plus negative 29, so maybe I should do minus 29 over d of x, which is x plus 4. Or we can also write p of x is d of x times q of x plus r of x, which in our case, 3x to the 3 plus 9x squared minus 5x minus 1 is x plus 4 times 3x squared minus 3x plus 7 plus negative 29, so I'll do minus 29. Finally, the remainder theorem. The remainder theorem says P of x equal to C is equal to R of x, which we can confirm. Okay. We decided way back when that C is actually -4, right? Because we have, we need it in the form of x minus C, so C is -4. C, I'll do the light blue for this example, C is -4, and R of x we found was -29. So what we need to show is that P of x, which is 3x to the 3 plus 9x squared minus 5x minus 1, well, P of -4 is 3 times -4 to the 3 plus 9 times -4 squared minus 5 times -4 minus 1, and it's supposed to equal -29. The reason we have the remainder theorem is not to confirm it. It's if we're able to find the remainder, then if we've confirmed it enough times, then we can say, well, I don't need to evaluate this thing. I just know that it's going to be -29. So here we're just confirming it, which we won't have to do always. -4 to the power of 3 is -64 times 3. So I get -192. -4 to the power of 2 is 16. So 9 times 16 is plus 144. 5 times -5 times -4 is -20. And then -1. So I get -192 plus 144 minus 20 minus 1. Hey, what did I do wrong? -4. It's -69. Oh, plus, thank you. Nick's on the ball. That's awesome. Okay. -192 plus 144 plus 20 minus 1. Oh, phew. Otherwise, we would have been hooped. Thank you, Nick. All right. We're all out of time, but what I want you to do is just work through these examples, just kind of as many as you can muster, and we'll go through some of these next day. Okay, so we just did this one, number 4, right? So do as many as you can of these. For next day, and we will go through some of them for review. Some of them for review. Okay, next day, I guess I should say. Okay, so make sure that you get really good at long division of polynomials. I know it's hard, but you need to keep working at it, okay? And then if you do find one that's a little bit trickier, maybe something like, something like this one, of course. How about we go through that one together? But if you find one that's hard that you want to work through together next day, then let me know. Any questions? Okay. All right. I haven't seen any questions. Thanks, Nick. Then I will see you on Thursday. Have a good day.